Dear friends, in this second part of the video we will continue the experiment started in the first part of the presentation, where we have seen the case of the double pendulum when the starting conditions have big angles and the motion is chaotic. In this part we will see that under different starting conditions, actually with small angles, the motion is not chaotic any longer and is predictable. We will see together the reason of that. In the beginning we introduce the problem, then we start the analytical study using the Lagrange method already developed in the first part of the video and adapted to this special case. We run the experimental phase to verify our findings. We display the results also by means of an animation. Finally, we resume our observations. In the video we will recall the part 1 very often to avoid useless repetitions.
This time we have the same mechanism, a double pendulum, but we limit the study to the very small swings, and therefore we can use a linear equation. We will see in the next slides how to come to that, and thanks to the linear equation we will argue that the solution is not chaotic any longer.
The dynamic problem we have solved already in the part 1 of the video at slides 4 and 6. We recall the findings. The potential energy V is a function of theta and phi, while the kinetic energy T is a function of theta, phi, theta dot and phi dot. The Lagrangian function L is the difference of T and V and has the following expression. The first motion equation is given by the Lagrange formula with partial derivatives with respect to theta. The second motion equation is written in a similar way with partial derivatives with respect to phi. Now we consider a linearized form of such an equation that is possible around a stable equilibrium point. The point we have already found at slide number 5 of part 1 and says theta equals 0, phi equals 0. The linearized Lagrange function we write with a star, and it is made by two functions, capital T star and capital V star, as the standard Lagrange function. But in this case, capital T star is a quadratic function of theta dot and phi dot, while capital V star is a quadratic function of theta and phi. In order to transform the function capital T star, we need to eliminate the dependency upon theta and phi. We use the Taylor series to represent the function cosine theta minus phi, with reference point the equilibrium 0, 0. We recognize that this development, arrested to the term of the first order, turns into 1. Therefore, the function capital T star assumes the form displayed in red. What about capital V star? Since capital V is a function of theta and phi, we apply the Taylor series to the whole function, this time till to the term of the second order, always starting from the equilibrium point. The term of order 0 is a constant, and we can assume this constant equals 0. Otherwise, it will disappear during the derivation. The terms of order 1 is 0 for definition of equilibrium, as seen in the first part of the video. It remains only the term of order 2, also the term containing the second derivatives. Those derivatives we have already calculated at slide 11 of part 1 and are here displayed once again. Definitely, the linearized potential energy capital V star assumes the form in red. By means of capital T star and capital V star, we build the linearized Lagrangian equation by calculating the derivatives of capital L star with respect to theta and phi and with respect to theta dot and phi dot. Finally, we calculate the derivative with respect to the time of the last two ones. With the above parts, we can build the two motion equations as we have done for the general case. We get the equations in red. We recognize that the equations are now linear and we can simplify them by eliminating the mass and dividing by L square. If we call capital A 4/3 of L, capital C L divided by 12 plus D square divided by L, then we can write the equations in an even more compact way. The great news is that now it is possible to solve the equations analytically. Let's see how. First, we replace the unknown functions theta and phi using a trigonometric function. We choose cosine. The two functions have same argument but a different amplitude. We call capital theta the amplitude of theta and capital phi the amplitude of phi. Both are functions of time with same frequency omega. We calculate the first derivative of theta and the first derivative of phi with respect to the time. Then we calculate the second derivatives and we observe that their expressions are equal to the function times negative omega square. Thanks to that, we can replace their values in the equations 1 and 2, obtaining a system of two linear equations in the only unknowns phi and theta. Also, no derivative appearing any longer. If we group the coefficients of theta and phi, we may write the system in a matrix form. The system is linear and homogeneous. That means are possible solutions different from 0, 0 only if the determinant of the matrix is 0. The determinant of the matrix is 0 if the following equation is satisfied. The solutions non-negative are 2 and correspond to the two frequencies of the system, omega 1 and omega 2. The general solution of the system is a linear combination of the single solutions, once written for omega 1 and once written for omega 2, while the amplitudes capital theta and capital phi can be found by solving the linear equations 3 seen in the previous slide by replacing omega 1 and omega 2 respectively. Since the equations are not independent, it is enough to use the first one after assigning to the amplitude capital theta an arbitrary value, for example 1. Thus we find the expressions of capital Phi1 and capital Phi2 respectively. To find the remaining four constant capital C1, capital C2, gamma 1, gamma 2, we use the four initial conditions. The first two, for the positions theta 0 and phi 0, give the following equations. The second, for the two velocities, in our case both 0, give the following two equations. From the second ones, we argue that the angles gamma 1 and gamma 2 are both 0. From the first two, we find the constants capital C1 and capital C2. We notice that omega 1, omega 2 and the amplitudes capital theta and capital phi do not depend upon the initial conditions. Let's start now with a numerical example. The starting angles are 10 degrees for both theta and phi. Using the geometrical data of the pendulum described in the part 1 and after calculating the constants capital A, capital C, omega 1, omega 2, capital phi 1, capital phi 2, which we remember do not depend upon the initial conditions, we may determine the coefficients capital C1 and capital C2. The angles gamma 1 and gamma 2 are both 0 as we have seen. We represent the solution in a chart. The angle theta is blue and phi is orange. We notice that the functions do not seem periodical. If we repeat the same calculation using the general non-linear model and we solve it numerically, we get a very similar chart. They actually overlap very well, and that justifies the linearized model. Let's see now what happens when we increase the starting angle to 20 degrees. We observe that the behavior is similar, but if we compare the two solutions, linear and general, the overlapping is not good. That says the linearized model is not any longer applicable. Let's judge now if the general solution for 20 degrees is repetitive or not. If we change the initial condition to 19 degrees, we get another chart that is well overlapping with the first one. The motion, even if not linear, is not chaotic. Same result we find with a starting angle of 30 degrees. Should we further increase the starting angle to 40 degrees, then the solutions are not overlapping any longer, at least the angle phi. That says the motion is not repetitive and tends to a chaotic behavior. In conclusion, we can say that the linear model is analytically known, being a sum of cosine functions. This solution is periodical and applicable for small starting angles. For slight greater angles, the equation is not linear, but the motion stays stable up to about 40 degrees. We said the solution is periodical, but how to find its period? The period of the single cosine functions, respectively capital T1 and capital T2, are given by the following formulas, while the period of the sum is the lean common multiple among them. That turns into 49.02 seconds. This period is common to both theta and phi and does not depend upon initial conditions. We run now the experimental phase and we repeat the trial twice, representing the outcome side by side with a slow motion 2, 2, 1. To identify the two trials, we marked the upper road with a ribbon of different colors, once pink and once green. It shows a substantial overlapping. Therefore, the motion is repetitive and not chaotic at all. We run here an animation of the double pendulum when starting condition 30 degrees. The animation has been achieved using the program GEOGEBRA and limited to the first 5 periods of theta. The theoretical and experimental values are matching almost perfectly, even though, because of the friction, the amplitudes of the swings decrease. That effect we have neglected in the model. The animation shows a substantial regularity of the motion, as we can see from the track of the point C. Final observations. For small angles less than 20 degrees, the system can be represented by a linear equation, the solution is periodical for both theta and phi. For intermediate angles from 20 to 40 degrees, the system cannot be linearized, the solution is not periodical, but the motion is predictable and repetitive. For great angles more than 40 degrees, the system cannot be linearized, the solution is not periodical, and the motion is chaotic. As a conclusion, we can say that the greater is the starting angle versus a steady equilibrium position, the less is predictable. The presentation of today has shown that the motion of a double pendulum under certain starting conditions can be repeatable and not chaotic, and also shows that under very small angles we can write the differential equation in a linear form having an analytical solution. This condition happens when the starting angles are close to a stable equilibrium configuration. In general, a dynamic system having 2 or more degrees of freedom, whose motion is described by a non-linear differential equation, can have a chaotic behavior. We remember that a chaotic behavior is something strongly depending upon the initial conditions. Also, in other words, a tiny change in the initial conditions produces a huge change in the behavior. I hope you have enjoyed this presentation. Let me know your comments and see you next time. Bye bye.